How long has it been since you had the flu? And do you know exactly how you caught it? For me, it's been about 2 weeks, and I'm 99% sure I caught it from a 7-year-old who coughed in my face. But a lot of times it's not so clear how we caught a virus. And while we know that many viruses are airborne, I'm curious if we have any idea how much virus might actually be in the air that's around us. And is there anything that we could do to maybe help mitigate some of that? Well, thankfully, Virginia Tech's Linsey Marr is an expert in this very subject and is working on a project that is on this very topic, and was kind enough to join the podcast to share all about it. Linsey is a University Distinguished Professor in the Department of Civil and Environmental Engineering at Virginia Tech. She leads the Applied Interdisciplinary Research in Air Laboratory, which applies an interdisciplinary approach to study pollutants in indoor and outdoor air. So Linsey and I talked a little about what we do and don't know about the pathogens that are in the air that's all around us. We also talked some about how we might be able to mitigate some of that, and a current project that she is collaborating with researchers all across the country on that could possibly one day end with us having a type of unit that automatically detects pathogens and helps clean the air. So if you too have been coughed on by a child returning home from school, I think this podcast might have a little hope to offer you. I'm Travis Williams, and this is Virginia Tech's Curious Conversations. As we're talking about air, and we're talking about air quality and aerosols and things that make us sick in the air, do we have any idea how much stuff on average is in the air that might be making us sick? And I'm not even sure what the right thing is to call that stuff.
Yeah, the stuff that's in the air that makes us sick, we call them pathogens, the stuff that causes infectious disease. But there's also other stuff that can cause asthma attacks, things like pollen, and we wouldn't really think of those as pathogens. But we did a study many years ago looking at the total amount of microbes in the air, and microbes include bacteria and viruses, and we were focusing on those. And we found in both indoor and outdoor air about 100 microbes or bacteria or viruses per liter of air. And a liter is like, a kind of a water bottle size. And so you're breathing those in all the time, but only some of them might be good for us. Some are totally harmless, and some of them might be bad for us. And so the amount that's in the air really depends where you are. And if there's someone who's sick, has the flu or a cold or COVID or something, and if they're coughing or talking a lot or singing, they could be releasing a lot into the air. And if you're in a poorly ventilated space, that could build up and you could be breathing it in, especially if you're closer to them.
Well, the other question that I was curious about is similar. Do we know how often? Is there any way to quantify how often when we get sick, it's because of stuff in the air versus like maybe stuff that we touch and ingest?
Yeah, that's a great question. That's like the $1 million question. One of the ones that's been driving my research probably for the past 15 years, and that's a huge open question, is how much transmission occurs by breathing pathogens that are in the air or by touching a contaminated object, like people think about doorknobs or door handles or maybe a tabletop that had a dirty tissue on it, or versus being close to someone while they're talking and they cough directly in your face, and some of those big droplets land in your eyes or in your nostrils or your mouth. And so we don't actually know. That is really hard to study with people because all of these different things can be happening at the same time, and you'd have to have a very tightly controlled experiment and regulate people's behavior in order to try to study this. So people have done modeling. For example, during the pandemic, there was a cruise ship where a lot of people became infected. It was called the Diamond Princess. People did modeling of that and found that maybe a third to a half of transmission they thought might have been occurring through particles, infectious virus particles that people breathed in through the air versus touching contaminated surfaces. There have been other studies in like hospitals, again, where they try to model it based on data and observations and like come up with kind of similar proportions. But there's so much uncertainty there. I think we still really don't know. And it probably depends on the pathogen. It depends on the type of environment you're in, whether you're in a hospital where they have really good ventilation, or if you're in a crowded bar or restaurant with tons of people and poor ventilation, and also on your own and other people's behavior.
Well, I'm glad at least it's a good question. Maybe not one that's as simple or has a simple answer, but that is what makes it a good question. I do know that I do know as a parent, having been coughed in directly in the face many times, I do feel like that upped my percentages of getting sick.
Yeah, that certainly does not help. I would say put that in the high risk category.
Well, I know one of the projects that you are working on right now is related to developing some sort of detection system, I think, for these pathogens that are in the air. And I believe, I'm going to try to read the name of it. I believe that it is called the Bioaerosol Risk Assessment Intervention Engineering Project, or BRAVE. And I want to know more about it. But first, I want to know, did the name come first or the acronym?
They came at kind of the same time. My research scientist or project manager and I were kicking around ideas, and we had a whole list of kind of words that we thought would be good in the title. And then we looked at the first letters and we tried some AI. But in the end, really, he came up with this. This is Dr. AJ Prusson, put things together. And, it was like, oh, brave, of course. That makes total sense because, this is a brave project we're undertaking because it's pretty ambitious.
Yeah, that sounds awesome. That just is a little bit more in my wheelhouse of activities, I think, at this point. But what is that project? What can you tell us about what you all are trying to accomplish in that space?
Yeah, this is a project that was being sponsored by the Advanced Research Projects Agency for Health, ARPA-H, and we are trying to develop kind of like a smart building system for that keeps pathogen levels low so that people don't get sick. So you could think of it like in buildings we have fire suppression systems where there's a smoke detector that's connected to some computer system that will then, if it detects something, it will turn on the alarm, of course, and then maybe turn on sprinklers in certain areas, have you close doors in certain areas. So that's kind of like what we want to develop for pathogens in the air. And so we have some kind of detector or sensor that would detect, let's say flu virus or the coronavirus or other viruses we're concerned about that can make us sick. Also fungi that cause allergy attacks or so you detect those in the air in real time, like maybe you're looking every 15 or 30 minutes or so. And if it does detect them, then you send that information to a kind of a computer system, that program that takes that information along with other information, like how many people are in the building, how much illness is there in the community, what are we seeing in wastewater, what do we know about what's going on in hospitals, what's the weather like, and puts all that information together and comes up with a risk level. So is the risk of people getting sick now in the building high, medium, or low? And if it's high, then it's going to automatically implement the sprinkler system for pathogens. So it's not really going to spray water, but it would maybe turn up the ventilation to help remove those pathogens from the air, turn on extra filtration, or turn on a certain type of ultraviolet UV lights to kill them, and bring that risk level back down to what we decide is kind of an acceptable baseline level. And it would do all this. It would do all this in the background, so it wouldn't require any action or thought by people in the building. So during the pandemic, of course, people are thinking about this all the time, and oh, do we need to do this or that? Turn on this, open the windows, or whatever. It would just do this. Nobody would have to think about it, and hopefully, we would all be in better health, have a lower risk of getting these types of diseases.
It almost sounds kind of like you have a series of detectors, like smoke detectors, but it almost sounds like it runs more like the air conditioning at my house with the thermostat, where it just
Exactly.
kicks on, keeps
That's
things clean.
exactly it. It's a thermostat where it's trying to keep the risk. A thermostat's trying to keep the temperature at a comfortable level. Our system is trying to keep the amount of bad stuff in the air at a low level.
Yeah, and it also, did you say that it incorporates kind of like what's going on in your community and in the hospitals, like what's
Yeah,
relevant?
there's a kind of a risk modeling part of it. So there's the information it gets from the sensor, which would be just, okay, are we seeing a lot of pathogens in the air? But it also combines, and that's one piece of information, but maybe it finds a slightly elevated level, but it's not like high enough to trigger things. But then it also knows that, oh, we have a lot of hospitalizations going on right now for flu or RSV, or we're seeing a lot of stuff in the wastewater. It would take that information to account and think, well, you know what? Because of that, we're going to be extra cautious here, and we're going to say the risk level is maybe higher than we would get just from the sensor. Or maybe alternatively, it sees, oh, these other levels are low. We know the building occupancy is low. we're gonna keep things down, because implementing those interventions does cost us energy. So we want to make sure we're not just driving costs through the roof.
Yeah. Well, that sounds like a lot, but I'm curious what the biggest challenges are in creating, implementing, inventing a system like that.
Yeah, I'd say that the biggest challenge, the biggest technical challenge is certainly the biosensor, trying to be able to detect pathogens in the air in real time. This is something that's, we've been trying, my lab has worked on for 15 plus years. We first proposed in probably 2007 or 8 that we would develop a real time sensor for flu virus in the air. And there's a lot of scientific papers that have been published where they claim to have developed some kind of fancy method that can detect pathogens in real time, but they haven't taken the final step of like implementing it in the real world and collecting an air sample. Like they can do it in the lab when they have a lot of, like, let's say the flu virus, and it's very pure and there's not a lot of interfering materials. But out there in the real world, okay, you need to collect this big air sample, which is not easy. The amount is dilute. Like if you're collecting a water sample, you just go turn on the faucet, collect it into your vial. Collecting air samples, you need to run a lot of air, and you'll pull it through maybe a filter where you're collecting things, or some other kind of collection device. You need noisy pumps to do this, so that's a challenge, as pedestrian as it sounds. And then you get your air sample, and maybe you transfer it into liquid, and now you have to take your liquid and apply it to your sensor, kind of like maybe a rapid test. Remember, you'd swab yourself, put it into a little bit of liquid, and you drip that onto your rapid test. Here, we also have the fact that in the air, there's not only all these other microbes in the air besides the one you're looking for, there are millions of other types of particles in the air, of soot or of salt-like particles, of tiny organic material. So for every one virus that you're looking for in the air, there's probably 1 million to 1 billion of other types of particles. So your biosensor has to be very, very specific and be able to sort through all the other stuff in order to find that one virus particle that you're looking for.
Yeah, it almost sounds like the second question I ask you is kind of the answer to this one, why it's so complicated. Just figuring out what is out here is really challenging. Well, I know that you are working in across institutions in this, and you have a lot of different collaborators. And so I'm curious with a project like this, what's the benefit of having like a multi-institution approach to a project like this?
There's a couple of different benefits. One is that from the sponsor, ARPA-H, they want us to demonstrate this technology in 3 different climate zones in the US. So we're not just demonstrating it near Blacksburg or in Washington, D.C. We're also demonstrating it in Sacramento, California, which is hot and dry, and also in Ann Arbor, Michigan, which is very, very cold. And so we need institutions around the country that bring that perspective of, oh, the climate here is very different. We have to think about very different things. We have different kinds of construction. We operate our buildings differently. So that's one thing. And then the other thing is that it is obviously very multidisciplinary. We've got electrical engineers, mechanical engineers, environmental engineers, epidemiologists, virologists, medical doctors, social scientists, computer scientists, just tons of different people involved. And for me, leading this project and putting together the team, actually, I was looking for the best research groups, whoever was kind of the best in that piece that we needed. And it'd be great if all that expertise were here at Virginia Tech, but in reality, there's different research groups or labs around the country where maybe I know, and I've worked with all of these people before in different projects. Okay, they're the best at developing this type of biosensor. They're the best at doing this type of computer modeling. This other group is the best, and they've thought a lot about buildings and energy and sensing in them. And so bringing those all together was really, I think, the best way to tackle this really ambitious goal that we have before us.
That's really fascinating. I didn't never even thought about the climate aspect and the weather and that playing a role in it. But it makes sense because even if we were just talking about air conditioning units, it would be vastly different in different areas. So that's a really interesting piece. Well, I guess with this project, what do you, I guess, hope? I mean, what's the hope for this project? What is, I guess, the end, maybe the dream result in your mind of the project?
I would say the goal that we had, that ARPA-H set for us, is very ambitious. And this is typical of these types of high risk, high reward projects. They'll set a goal that's so far, a line in the sand, that maybe at this time and with the resources you've given, it's a real stretch to try to get there. But even if you get partway there, you've gone a lot farther than you would have otherwise. So my goal is to have some kind of system with rapid detection of some pathogens. They would like us to be able to detect 25 or 100. I don't know if we need to detect that many different types of pathogens, but to detect at least a few of the key ones, and be able to tie that into building engineering systems to ensure cleaner and healthier air. And so to really take what has been shown in the laboratory for years and to get it out into the real world. So that's that we have, you know, easier access to cleaner air for more people.
Yeah, I think that sounds great. I think my dream for your project right now, just because I'm thinking about the kid that I have here, is that if he walks in the house, everything kicks on and just sucks all the germs out, like away from him.
Yeah, or you
Out
think
and
about
sticks them
kids.
outside.
You think about kids going to daycare or school. I always, when my kids were younger and they were going to daycare, I felt like I was sending them to the germ zoo and they were going to come back with stuff. And it would be great if that germ zoo were not a germ zoo, where if where I was sending them was actually a place with cleaner air than they would get otherwise. And then I know that they're less likely to come back sick, less likely for them to get sick, less likely for them to can have to miss school and work and all that.
Yeah, well, all of that sounds great. Well, I am curious, maybe more on like a practical level. You've been in this space studying this type of stuff for a long time at this point. I'm curious, what's one thing that maybe you have put into practice from your research that maybe you would have never thought about had you not gone down this road?
Yeah, I think I've, over the recent years, have realized the power of the portable air cleaner or air purifier that kind of gained recognition during the pandemic, because I talked about them, but I didn't have one. Now we have one in the house and we use it a lot, not just when people are sick, but also when we're cooking, and because cooking creates a lot of particles in the air. And it's really surprising to me to see how high the levels get sometimes from cooking. But between that, or if we have bad wildfire smoke days, we'll run it. Or let's say we're using the wood stove and we have creates a little bit of smoke that gets into the house, we'll use it. And certainly when someone's sick, we'll kind of have it follow them around the house. And my sense is that it's led to less transmission of illness in our family. So that's one kind of practical take home thing. And it's a matter of getting it doesn't have to be a HEPA air cleaner, but something that's a good quality filter and that runs at a high enough clean air delivery rate for your space. And there's places where you can look at calculators to figure out, okay, how big is my room? How big of an air cleaner do I need?
And thanks to Linsey for helping us better understand airborne viruses and the potential for cleaner air in the future. If you or someone you know would make for a great Curious conversation, email me at traviskw@vt.edu. I'm Travis Williams, and this has been Virginia Tech's Curious Conversations.